Welcome back to the second part of our lecture today. Now, when we left off, I was talking about this result of Lantos, namely that there exists an equilibrium price that you can assign to each of the sectors, so to each of the outputs, so that the income of each sector balances expenses. So what this means is that electricity, steel, and manufacturing can set its price so the amount that it spends is equal to the amount of money that it gets, and that would be true for each of the three different sectors. And this will actually hold much more generally. Now, up to now, we haven't really seen where linear algebra comes in. And that's what I want to do for the rest of this part of this video is show you how linear algebra can be used to find the equilibrium value that should exist according to Lantos' result. So way to do this is, first of all, we want to look at each sector and try to figure out how much it purchases from each of the other three sectors. So for example, manufacturing purchases 30% of the output of manufacturing. It purchases 40% of electricity, and it purchases 60% of steel. Electricity purchases 30% of manufacturing, 10% of electricity, and 20% of steel. And steel purchases 40% of manufacturing, 50% of electricity's output, and 20% of steel's output. So already we're starting to see that linear algebra may come into play because it looks like we have some sort of matrix here. But in order to make this a linear algebra problem, we need some variables, and that's what I have down here. We're going to let PM be the price of manufacturing. So that's how much manufacturing should set its total output to. So how much should it charge for its total output? Electricity, the same thing. PE will be the price of electricity, and PS will be the price of steel. So we're interested in knowing what are the values of PM, PE, and PS so that we get a balance or an equilibrium between the three sectors. Now, one thing that we should notice is that each row in this table is actually giving us a cost equation. Okay, so for example, each row in the table gives us a cost. So for example, row 2 implies that electricity spends the following amount. It spends 30% of whatever the value of PM is worth. Plus it spends 10% of whatever the output of electricity is worth, plus it spends 20% of whatever the value of steel is. So this is the cost equation for electricity. And now our goal is we want our cost, right, to be equal to its output, which is its price. So we get an equation, and in fact we get what looks like a linear equation that we want our cost to be equal to its price. So we are doing electricity. So we want electricity, this is the total value of its output, to be equal to its costs. So basically it makes no money, but it manages to cover its costs exactly. So we can repeat this, I can do both on the same slide here. Each row here gives me a linear equation. So this is coming from the table, and then we're setting them equal to these things here. So this is the price of each sector. And we can rearrange each of these equations so that we have all the variables on one side and what it's equal to on the other side. And amazingly, at the end here is we're getting a homogeneous system of linear equations. So we want to be able to solve this homogeneous system of linear equations. Now we know that there is always at least one solution, namely the trivial solution. So the question is whether there is another solution or not. So I've written below the augmented matrix, or not the augmented matrix, just the coefficient matrix of this system of linear equations, homogeneous system equation. So I need to row reduce it. Now, luckily, I could do this by hand, but it will take a little bit of time. So instead, I'm just going to go pop over to Octave. And let me reconnect. I had it all set up, but I'll just redo it again. So I'm going to input my matrix. So negative 0.7, 0.4, 0.6 for the first row, 0.3, negative 0.9, 0.2 for the second row, and 0.4, 0.5, negative 0.8 for the last row. Okay, so there's the homogeneous matrix, and I want to find its row-reduced echelon form. And there we go. This is my row-reduced echelon form. So let's go back to my slide. And we'll go back to full screen here. And I'll write out what the output was from the octave. So that was 1, 0, and negative 1.21569, 0, 1, negative 0.62745, and 0, 0, 0. So what we see, using the knowledge that we have from our previous lectures, is we have that PE is free. Oh, sorry, not E, S. S is our free variable. So PS is free. So because we have a free variable, there is a solution to this homogeneous system that's not the trivial solution. And we also get that PE is equal to 0.60, sorry about that, let me clean that up, 0.62745 times whatever the value of PS is, and the manufacturing is 1.21569 times PS. Okay, so kind of summarizing it, what it means is that all solutions to this homogeneous system equations have to form a PS times this particular vector. So let's step back for a second and explain exactly what we have here. Okay, so let's say that the steel industry has knows that its total cost, or the amount of money that it brings in, is $10 million. Right? Then if the output of manufacturing is $12,156,900, and electricity is 6,274,500. So really, where do these numbers come from? If I set this number to 10 million, that's going to tell me what the PM is and then the PE is by the appropriate scaling. So if steel makes $10 million and manufacturing makes $12.1 million and electricity makes $6.2 million, then each sector makes exactly enough to pay off all of its costs. To pay off all of its costs. Okay, so this is giving you an example of Lantos input-output model. Okay, let's go back over here, which says that you can always find an equilibrium. So basically what Lantos observed is that you can cook up a homogeneous system of equations like this, and no matter how your sector is divided up, you will always be able to find a free variable, and once you have that free variable, you're able to find a solution that allows you to balance everything. So that ends our economic example. In the next part, we'll look at a different example coming from network flows.